गुड इवनिंग सर।
यस आयुष, गुड इवनिंग। लास्ट डे कौन सा टॉपिक डिस्कस किया था हमने?
सर के केमिकल बॉन्डिंग कर रहा था सर।
तो केमिकल बॉन्डिंग हो गया का?
आज मतलब सर सॉलिड।
हाँ, कंप्लीट हो गया।
यस सर।
आपके कौन कौन से टॉपिक हो गए?
यस सर। मतलब सर जो मेरा फर्स्ट हुआ था सर वो रिएक्शन मैकेनिज्म हुआ था। उसके बाद सर कोऑर्डिनेशन हुआ था। उसके बाद सर ऑर्गेनोमेटेलिक्स हुआ था। और फिर उसके बाद सर केमिकल बॉन्डिंग हुआ था। और सर अभी सॉलिड स्टेट है, मतलब चल रहा है। मतलब सर अभी मतलब स्टार्ट ही होगा अभी।
अभी आज से स्टार्ट होगा।
यस।
आपका इंटरव्यू कब है? 7 तारीख को।
हाँ यस सर 7 को।
स्टार्ट करते हैं हम। व्हाट इज
यस यस।
सॉलिड स्टेट? व्हाट द बेसिक प्रिंसिपल ऑफ सॉलिड स्टेट इन केमिस्ट्री?
यस सर। Sir, generally, the solid are the substances which have the definite arrangement of the constituent particles, and they have their definite shape and the definite geometry. And basically, solid can be converted, classified into the two types, that is the crystalline solid and the amorphous solid. And there are also the various types of solid like the covalent solid, ionic solid, metallic solid. Yes,
क्रिस्टलाइन सॉलिड, एमोर्फस सॉलिड में क्या डिफरेंस है?
yes. So the crystalline solids are the true solids, sir, basically, and the amorphous solids are not the true solids. And the crystalline solids have the constituent particles that are orderly arranged. But in case of the amorphous solid, the constituent particle are not orderly arranged. And in case of the crystalline solid have the sharp melting point, but the amorphous solid melts over the range of temperature. And also the crystalline solid shows the property known as the isotropy. Means no, the crystalline solid shows the property known as the anisotropy. So in case of anisotropy, the properties on going in the different direction does not remain the same. The properties like the refractive index, electrical conductivity are not same when we move in any direction. But in case of the amorphous solid, they show the isotropy, means the properties remain same in any direction when we move. And also in case of the crystalline solids, the graph the when we cool the substance, they do not show the smooth cooling curve in case of the crystalline solid, but the amorphous solid shows the smooth cooling curve, the smooth cooling curve. And the example of the crystalline solids are the NaCl, CSI, or the CSCl. And the amorphous solid has the example like the rubber, tar, uh, plastic are the example of the amorphous solids.
Yes, what is a molecular solid, ionic solid, metallic solid, covalent solid? What is this?
Yes, yes, sir. Yes, yes, sir. So the first one is the ionic solid. So the solid is basically classified on the basis of their molecular arrangement in the lattice. So the first one is the covalent solid. The first one is the ionic solid here. So in case of the ionic solid, the two different cations and anion, for example, Na plus and Cl minus, are arranged in the space lattice to form the ionic solid. So, for example, in case of the NaCl, uh, so the Cl minus here shows the FCC structure, and all the Na plus are occupied in the octahedral void. So this octahedral void is basically present in the uh, edges of that cube and in the body center. So so in case of the ionic solid, basically the positive charge, that is Na plus, is surrounded by the negative charges, that is the Cl minus. And here the coordination number for the NaCl is basically 6:6. So this is the example of the NaCl. And the ionic solid basically shows the defects, that are the Schottky defect and the Frenkel defect. And And moving further, that is the molecular solid. So the molecular solid is divided into the three types. So the first one is the non-polar molecular solid. Second one is the polar molecular solid, and the third one is the hydrogen bonding molecular solid. So the first one is that. Yes, sir. So the first one is the non-polar molecular solid. So here the forces that exist between the non-polar molecular solid are basically the London forces or the dispersion forces. So its example is the helium gas or the neon gas or the H2Cl2. So these compounds uh, exhibit the non-polar molecular solid. But in case of the polar molecular solid, so there is basically the dipole-dipole interactions between the two solids. For example, HCl, so and SO2. Here they show the dipole-dipole interactions. So in case of the polar molecular solid, the boiling point or the melting point is higher than the non-polar solid. Here, in case of the non-polar solid, the boiling point is very less. But in case of the polar molecular solid, the boiling point is somewhat higher. And the third one is the hydrogen bonded molecular solid. So the hydrogen bonded, basically this solid shows the hydrogen bond in between them. For example, NH3, H2O, they show the hydrogen bonding in them, and they have the higher boiling point as compared to the first two. And the third one is the covalent solid, basically. So these covalent solid are basically the solids which show the covalent bond in them. For example, diamond, graphite. So they show the covalent bond in them, and these are the strongest solid. So they are brittle, but they are very hard. The covalent solid are normally non-conductors of electricity, except the graphite. The the graph of the different layers which slides on one another. And the fourth one is that, and the fourth one is the metallic solid. So the metallic solid is basically made up of is basically prepared by the metals here. And here the ionization energy of the metal is very low. So the metal loses its electron easily. So it forms the cation. For example, Na plus, which is surrounded by the different electrons. So it is like the electron are moving in the sea of the metal. So it can easily conduct the electricity. So it is a very hard solid, which is the metallic solid, and which can conduct the electricity. So these are the different types of solids.
Yes. What the example of molecular solid, ionic solid, metallic, covalent?
Yes, yes, sir.
Yes.
So the example of the ionic solid is basically any ionic compound that is NaCl, or the which we call as rock salt or the sodium chloride. Another one is the cesium chloride. Uh, Next one is the ZNS, zinc sulfide, like this. And the example of the molecular solid is basically, so the molecular solid is distinguished between the different types. For example, the non-polar molecular solid has the example like any neon, argon, H2, Cl2 are the example of the non-polar molecular solid. The examples of the polar molecular solid are basically the HCl, SO2 are the example of the polar molecular solid. And the example of the hydrogen bonded molecular solid are basically water, ammonia, HF, the compounds which shows the hydrogen bonding basically. And the example of the covalent solid is basically the example of the covalent solid is basically the diamond, graphite, graphite,
Yes.
diamond, and the graphite. But in case of the metallic solid, the examples are all metals and their alloys. For example, alumina. So this all exhibit, or the ZNO. This all exhibit the metallic. Uh, so these all are in the form of the metallic solid. Yes, sir. All metals and their alloys, sir. Alloys.
Yes, what is a primitive unit cells in solid state? How many types?
Yes, yes, yes. Yes. So the primitive unit cell is basically the cell in which the atoms or the constituent particle are present only at the corner. So they are not present in any of the faces or in the body centered. So the example of the primitive unit cell, so it looks like this. Basically, the primitive unit cell. Here, the constituent particles are present only at the corners here. In case of the primitive unit cell, and here the contribution is only uh, 1/8 of the contribution is only here. The 1/8 only gives 1/8 of the contribution. So here the atoms, that is whole atom that is present, is 1/8 into the 8. So only one atom is present in case of the constitutional, in case of the primitive unit cells. And there are the different unit cell like the primitive body centered, face centered, and end centered, sir.
Yes, types primitive unit cells is cubic, tetragonal,
Types, sir, what, sir?
cubic, tetragonal, orthogonal, hexagonal, rhombohedral.
Yes,
All
yes, yes, sir. So, sir,
types.
the primitive unit cell is present in all the systems, sir. So it is common in all the systems, sir. Means in cubic, tetragonal, rhombohedral, monoclinic, triclinic, and the yes, sir.
Yes, can you explain one by one? What the main application of
Yes, sir.
these solid state?
Yes, sir. Main application is yes. So in basically in the solid state, sir, we look at the different arrangement of the solid. So, for example, the cubic system that can be divided. So, for example, the first one is the uh, so the first one is basically the cubic. Then second one is the uh, tetragonal or orthogonal. Third is the rhombohedral, monoclinic, triclinic, hexagonal. 1, 2, 3, 4, 5, 6, 7. Cubic, uh, orthogonal, rhombohedral, monoclinic, triclinic, hexagonal. Cubic, orthogonal, rhombohedral, monoclinic, triclinic, hexagonal. Rhombohedral, I guess here. Rhombohedral.
Yes.
The cubic, tetragonal, uh,
Orthorhombic,
orthogonal,
hexagonal,
monoclinic,
rhombohedral,
hexagonal.
monoclinic, triclinic.
Yes, yes, yes. And the
Can you explain one by one?
rhombohedral. Yes, yes. So these are basically the 7 crystal systems. 1, 2, 3, 5, 6, 7. So here in basically uh, A is equals to so here the age side, here the A is equals to B is equals to C. So basically row 1, 2, 2, 2, 1, 0. So here all the sides are same in case of the cubic, but in case of the tetragonal, here one side is different. In case of the orthogonal, so all the 4 sides are the different here. In case of the monoclinic also, all the 4 sides are different. In case of the triclinic, is all the four 3 sides are different. In case of the hexagonal, only one side is different, and in case of the rhombohedral, all the sides are same. So if you look at their angle, so in case of the cubic, all the angle is equals to 90. In case of the tetragonal, all the angles are equals to 90. In case of the orthogonal, all the angles are equals to 90. In case of monoclinic, so this triclinic is the least symmetric. So alpha does not equals, so all the angles are here the different. In case of the hexagonal here, alpha is equals to beta 120. Alpha and beta does not equals to 90, and gamma equals to 120. And in case of the rhombohedron here, and in case here alpha is equals to beta is equals to gamma does not equals to 90. In case of monoclinic, sir. Yes, sir. Rhombohedral. So I'm not getting it correctly, sir. Here.
Rhombohedral A is equal to B is equal to C, alpha, beta, gamma 90.
Yes, sir. Alpha. Yes, sir.
Yes, what the example of these one?
सर इसके एग्जांपल नहीं करे सर मैंने मतलब एग्जैक्टली
Yes, cubic example is NaCl. Yes, tetragonal example is TiO2. Orthorhombic example is rhombic sulfur. Hexagonal example is graphite, zinc oxide, cadmium sulfide. Rhombohedral example is mercury sulfide. Monoclinic example is monoclinic sulfur. Triclinic example is CuSO4 into 5H2S3BO3.
yes sir
Yes, what the main purpose of these one in solid state? Primitive unit cell.
yes sir the primitive unit cell is basically the simplest unit cell. So with the help of unit cell we can tell about the interplanar distance, that is a d interplanar distance between the two definite layers, sir. So and with the help of the primitive unit cell we can find out the number of the atoms that are present in that crystal system, sir.
Yes. What is body center unit cell?
Yes, sir. So the body centered unit cell is basically the unit cell in which all the constituent particles are present at the corner as well as the one particle is present at the center. So basically it looks like this. So this is the body centered unit cell. So here the particles that are present, here the 8 particles are present at the corner which contribute 1/8. So it becomes 1, and the one particle is present entirely at the body center, so its contribution is a whole atom. So here the 2 atoms are present in the BCC type of structures total.
Yes, example of BCC.
So example of BCC, sir, is the cesium chloride is the example of the BCC, sir. Cesium chloride, sir, which has the coordination number of 8. Here, sir, this cesium atom occupies in the central, and the chlorine ions are present at all at the corners, sir. So this is the example of the BCC, sir.
Yes. What is FCC? Base center cubic unit cell.
Yes. Sir, in case of the face centered, so it's the best example is the NaCl basically. So here we can see that in case of the FCC unit cell, here the all atoms are present at the corner basically, and the face centered. So here I have taken the Cl minus, which is present at the face center. So here we can see that 1/8 of 8 particles are present at all the 8 faces, which have contribution 1 by 8. Plus we have the 1, 2, 3, 4, 5, 6 faces which have 1 particle. Here the contribution of the 1 particle is 1 half. So here we can see 1 plus 4 particles of Cl minus are present in case of the FCC lattice. So its example is the NaCl is its example basically. And here the Na plus is present in the octahedral void basically. So this octahedral void is present in between this edge length. So I am showing the octahedral void by this cross sign. So here we can see that Na plus is, so here we have the edges, that is 1, 2, 3, 4, 4, 4, 8, 12 into 1 by 4, that is 3 plus 1 at the body center. So here the 4 Na plus and 4 Cl minus are present, sir. So it is the example of the FCC.
Yes, what the difference between BCC, FCC, simple cubic, primitive unit cell?
Yes, sir. So the difference between basically the primitive, so which have the atom only at the corners, so it is basically the primitive. So it has only at corner atoms. If we take the another one, that is the BCC. So BCC has the atoms at its corners as well as in the body center. So it is the simple primitive. It is the body center, and it is the FCC basically. So here in case of FCC, atoms are present at the corner as well as the face center. So here we can look at the face center. So if we talk about the packing fraction, in case of the BCC is 52%. In case of the simple primitive, it is 52%. In case of body center, it is 68%. And in case of the FCC, it is the 74%. So we can see that the most compact cell or the is the FCC cell, which is the most compact basically as compared to the body, as compared to the body center and as compared to the simple primitive. Here in the simple primitive, only 1 atom is present. In case of the body center, we are having the 2 atoms are present, and in case of the FCC, the 4 atoms are present. So the packing fraction here, so the void is less in FCC as compared to BCC and the simple primitive, sir. And also and here also the interplanar distance is low in case of the FCC as compared to BCC and the simple primitive here. Yes, sir. And here the distance of A, which is the distance, is different in each case also, sir.
Yes, right. But the difference between SCP and CCP, what the meaning and what the
Yes, sir.
formula, what the uses, application, SCP and
Yes, sir.
CCP.
HCP and CCP. So here HCP is a hexagonal close packing, and the CCP is basically the cubic close packing. So here for the CCP, we can also say it as FCC. So the CCP and FCC are the equivalent, which have the packing fraction of the 74%, and it is also hexagonal close packing. So it is basically present in case of the compound like the zinc sulfide, which is showing the Rootzeit and the zinc blend structure. So HCP is basically hexagonal close packing. So here the molecule are arranged like this, basically in a hexagonal order. So in case of so so it are arranged like this, and in case of FCC, CCP, it is the same like the FCC, which I have explained earlier in case of NaCl. And sir, HCP is basically present in case of the zinc group side structure, sir. But I have not studied it clearly, sir. In case of HCP, means that much depth I have not seen in case of HCP, sir.
Example of SCP and CCP.
Sir, the example of the HCP is basically the root side structure, sir, of the ZNS, in which the Zn2 plus occupies one half of the tetrahedral, and the sulfur 2 minus are present in the hexagonal close packing, sir, I guess. And sir, FCC, CCP and FCC are the same. So we can take its example as NaCl. CCP's example, sir, we can take it as NaCl. And in case of HCP, we can take its example as the root side structure, sir, of the ZNS, in which the zinc 2 plus are present in one half of the tetrahedral, and the sulfur 2 minus are present in the hexagonal close packing, sir. But I'm not that much pretty confirm about this, sir, ZNS.
Yes. What is point defect in solid state?
Yes, sir. So the point defect is basically the defect at the particular point. Uh, so, so in the solid state, we are having the crystal lattice, or the space lattice, that is made up of the different constituent particles. So the defect at the particular point, we call it as the point lattice. Sorry, the point defect. And the point defect is divided into the two types. That is the Frankel defect and the point defect. So this point defect, we can uh, we can classify it into the two types. That is the stoichiometric defect and the non-stoichiometric defect. So in case of the stoichiometric defect, we can see the Frankel defect and the Schottky defect, sir. So the point defect is basically the defect at the particular point in the crystal, sir, and it is different from the uh, line defect, sir.
Yes. What is stereometric defect?
Yes, sir. So the stoichiometric defect is basically the defect in which the after the imperfection in the crystal, the same number of the cation and anions are present in the crystal lattice. So we call it as the stoichiometric defect, in which after the defect, the cation and anion that is present in the crystal are the same. So the electrical neutrality is attained in that crystal. So it can be defined into the, for example, the first one, we can take it as the Schottky defect and the Frankel defect. So which we take or consider it as the stoichiometric defect, sir.
Yes. What the example of Frankel and Schottky defect?
Yes, sir. So this Frankel and the Schottky defects are basically seen in the ionic solids, basically. So if we consider the Schottky defect, so here we can see basically, so this is basically the lattice with its different constituent particles which are arranged in the space. So here we can see in case of the Schottky defect. So here the same number of cation and anion are missing from the lattice, basically. Here A plus, B minus, B minus, B minus, A plus, B minus, A plus, A plus, B minus. So here we can see this plus point and minus, that is we can see here. So so here these two particles, that is plus and minus, are absent in case of the Schottky defect. So here the density of the crystal decreases, but it is electrically neutral because the positive and the negative charge are absent in case of the Schottky defect. But in case of the interstitial defect, here I will take the example of the interstitial defect. Interstitial defect. And I also want to add something in case of the Schottky defect. So the Schottky defect is seen in the compound which are having the high coordination number, and also the size of the cation and anion are somewhat comparable. Then they show the Schottky defect. But in case of the interstitial defect, here basically the cation is dislocated here. Only the cation is dislocated from its position. So it occupy another interstitial site in case of the Frankel defect. So here the vacancy is created, and the compound which shows the interstitial of the Frankel defect basically have the low coordination number, and the cation size is smaller as compared to that of anion. So they show the Frankel defect here, and here the density does not changes in case of the Frankel defect, sir. And the example is AgBr, all the type of the silver halides, because the Ag plus, the size of the Ag plus is smaller, so they can easily be dislocated from its position. So they show the defect, that is the Frankel defect, sir. Yes, sir.
Yes. What is metal axis defect?
Yes, sir. Metal axis defect is. So the metal axis defect is basically we can take it as yes, metal axis, sir.
Yes.
So sir, here are basically the two conditions. Here basically the first one we can take it as the onion leaves from the crystal lattice, and the second condition that we can take is it can be the so I consider here the first case. For example, we are having the any crystal which is the NaCl. So when the sodium vapors are passed over the NaCl, vapors are passed. So here what happened? This Cl minus get diffused from the NaCl crystal, and it reacts with the Na vapor to produce NaCl outside the crystal. So here vacancies are created in NaCl. Here vacancies are created in NaCl, and these vacancies are occupied by the electrons basically. So we call this defect as the metal axis defect. So it is due to the anion leaves from the crystal lattice. And the second one which we can consider is basically, for example, we are having the any compound which is like the zinc oxide we are having, and when it decomposes at the high temperature into Zn2 plus 1/2 O2. So here excess of the cation are made in the in that crystal. So it is also the metal excess defect. So these are the two types basically. Anion leaves from the crystal lattice. Then one defect is created which is called which we call as the metal excess defect, and another one is when the decomposition of ZNO is happening, for example. So here Zn2 plus is forming extra. Yes, sir.
That's good. What is electron rich impurities and electron deficient impurities? What's the difference? What are the examples of?
Yes, sir. Yes, sir. Yes, sir. Sir, basically the impurities. Yes. sir, the basically the impurities are basically added into the any of the metal, so which we call as a doping, which we call as a doping. So for example, here the, सर इको हो रहा है क्या आवाज मेरा?
नहीं, आपका आ रहा है क्या?
So here basically, yes, yes, sir, here in basically the doping which is seen in case of the group 14 element. So for example, the carbon and the silicon, so they are doped with either group 15 element, that is the nitrogen, phosphorus, arsenic, and whether they are doped with the boron, aluminium, or the gallium. So when they are doped with this type of element, we call it as the N type of semiconductor, N type semiconductor. And when they are doped with the boron or the aluminium, we call it as the P type of semiconductor. So here we can see that in case of the P type of semiconductor, here only the 4 valence electron are present in case of the carbon, but here boron contain only the 3 valence electron. So we call it as the, so it basically create the holes in the crystal lattice. So it is basically the electron deficient compound is prepared, but here it can conduct the electricity because the hole can be transferred from one place to another. But in case of the N type of semiconductor, it is the electron excess defect, because here it has the 4 valence electron, and when one silicon is replaced with one arsenic, here basically it has the 5 valence electron. So here one extra electron is there. So it is basically the electron excess defect. So here we can see its band basically. So, so it is basically the valence band and the conduction band. So it is basically the valence band, and another one is the conduction band. So in case of the P type of semiconductor, so here the acceptor band is present close to the valence band, acceptor band. But in case of the N type of semiconductor, basically here the valence band and the conduction band. So here the donor band is basically present here, close to the conduction band, sir.
Yes. What the difference between conductor, insulator, semiconductor? What the difference?
Yes, 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 yes. So in case of the conductor, basically, if we see its diagram, basically, so here we can see that so this is basically the valence band, and this is basically the conductance band. So these both bands are overlapping on one another in case of the conductor, so they can easily conduct the electricity. But in case of the semiconductor, basically this conduction band and valence band are separated by a very small difference. So by creating some defects or the vacancy, we can convert semiconductor into the so we can easily, here the electron from the valence band can be transferred to the conductor band or the conduction band. But in case of the insulator, here the distance between the conduction band and the valence band is so large that it cannot uh, transfer its electron. Sir. Yes.
Yes, good. Yes, good work. Next day जो last part है उसको हम डिस्कस करेंगे. Types of N-type
Yes, sir.
conductor, इसके uses, application, limitations. ये जो बचा हुआ पार्ट है, मैग्नेटिक,
Yes,
फेरोमैग्नेटिक,
sir.
फेरोमैग्नेटिक, ये सारे टाइप्स एग्जांपल्स हैं सॉलिड स्टेट.
Yes, sir.
Demographic, magnetic moments, how to determine. बाकी और